Okay, this is a revision of the last lecture that I did on RC time constants. The previous one, I don't think was clear enough, so um, I'm redoing it here. The purpose of this laboratory exercise is to familiarize you with the time constants in resistor, capacitor, RC circuits. It'll give you practice on calculating the time constants of an RC circuit. So the things we need for this experiment are a power supply, resistors, capacitors, a multimeter. The current meter is not really necessary, but it may be helpful, and just a proto board. So some general comments. For each of the circuits, use 5 volts. You could use 10 volts. I think in the lab we actually ended up using 10 volts. You want to select large resistors and large capacitors. And if you look, you'll see why 100,000 and 470 microfarads, that's probably a little too big. 47 seconds to wait for a charge. You're going to be, well into the minutes to see the whole charge cycle. So something like 10,000 ohms and 470 is 4.7 seconds. Somewhere around there, 10,000 ohms, 470, 330, 100 microfarads might be a little fast, but you want to use large values. I can probably dismiss this since you don't need to see me, you just need to see the text. Okay, consider this RC circuit. Here I've changed it a little bit for the last time. I put 2 meters, and 2 meters are only needed if you're using a multimeter that is bidirectional. You only need this one. But if you're using a physical galvanometer type meter, you have to have both of these because in the charging, the current will be in this direction, but in the discharge, the current will be in this direction. So you need to reverse polarity of the ammeter, and this switch will do it. So let's read the general. You consider this circuit with the switch open, nothing happens. With the switch closed, you get current through the capacitor, through the resistor, and back to the battery. So the current flow is in this direction. If you switch it to this position, then this takes the battery out of the circuit, and this is your current path here in this direction. The time it takes to charge and discharge the capacitor is determined by the constant tau, which is the product of the resistor value and the capacitor value. Let's do an example of the resistor, 56 kilo ohms and 330 microfarads. You can see the tau, the time constant, is 18.5 seconds. I've already explained this part about why there's 2 ammeters in the direction. Let's go to the discussion. Okay, so now we're showing the closed charging circuit. Once the switch is moved to the charge position, that is connecting it to the battery as shown in figure 2, the far left side, the current will begin to flow through the resistor, and charge will begin to build up on the capacitor. The rate of current flow in the circuit and charge buildup in the capacitor are nonlinear, as shown in figures 2, B, and C. As the charge builds up in the capacitor, the current begins to decrease until it finally stops. So here's the voltage. The voltage across the capacitor increases. The current through the resistor decreases. Notice here in the title I have charging and discharging. We actually use this. We'll see the same effect for both. The difference is that the current will be in the opposite direction for the discharge. Okay, so the voltage across the capacitor increases according to this formula. V across the capacitor is equal to the power supply voltage, V0, times 1 minus e to the minus t over tau. So V0 is the power supply voltage. E is approximately 2.71828, which is the exponential constant, the base of the natural logarithms. And tau is equal to RC. Note that at 1 tau, that is one time constant, the voltage across the capacitor has reached 63% of the maximum voltage. At 2 tau, 86%. And at 3 tau, it's reached 95% of the maximum voltage. It's a little hard to see on this graph. Let me do a new share with the Mathematica to produce. Here's the Mathematica. There, I think this should be a little clearer. There's the 60, the 67. I'm sorry, the 63%. Here's the 86. 87% is 86.5, as you can see here in the Mathematica. 95 here, and of course we get to 100. We're not quite at 100 at 6 tau, but we're getting close. So you can see that this is a nonlinear increase. These time steps are linear. They're not in seconds. They're in intervals of tau. So the how many seconds 1 tau is dependent on your time constant. But this is a little more visible. And you can see this is the charging discharge. Here we're at 100% when your capacitor is fully charged. When you flip the switch, within 1 tau, you're down to 36.8% of the initial current. Then at 2 tau, 13.5. And at 3 tau, 4.98, and I think that's all I did. Now, for discharging, the voltage looks the same: 36%, 37%, 13.5 or 14%, and 5% at 3 tau. Now let's go back to the. Let's see, where is it? I think it's this one. Yes, that's where we were. Okay, so that's got a better look at these charts, but let's discuss this. Well, first we'll discuss the current, and the voltage. The voltage for the discharge is going to look very similar. Current is equal to V0 over R times e to the minus t over tau. And we already went through these percentages, but let's look at this equation. Let's put the equation 1, that's this equation here. Let's put this equation into y equals mx plus b form. So we just distribute the V0, so you get Vc equals V0 minus V0 e to the minus t over tau. Let's bring this V0 over to this side. Vc minus V0 equals minus V0 e to the minus t over tau. Now, all I'm going to do here is multiply by -1 or to both sides, which reverses this V0 minus Vc and equals, it takes the minus from this side of the equation. Now let's take the natural logarithm of them. Natural logarithm of this side, and we get the natural log. Whenever you have a log of a product, it's the sum of the logs. So it's the natural log of V0 plus the natural log of e to the minus t over tau. So the natural log of e to an exponent is that exponent, and that's where we get the minus t over tau here, and we're left with the exponent is minus t over tau, and this would be the what remains, the ln over v. And so this is your y equals mx plus b. The x in this case is t, so the m is minus 1 over tau, which is equal to minus 1 over RC. Now, generating a plot of ln VO minus VC, V0 minus VC versus T, and producing the best fit line will give a slope of M equal minus 1 over RC. Therefore, tau is equal to the negative inverse of your slope. So whatever your slope is, you take the negative inverse, and you'll get your tau. Discharging, when you flip the switch, now the current goes in this direction. Discharge, this is the voltage. The voltage decreases and the current decreases. Now the current looks the same as above, but in this case, it's going in the opposite direction. And we can do the same analysis that we did above for equation 3. Vc equals V0 e to the minus t over tau. Take the logarithm of both sides, and we'll come up with a similar process. We'll come up with a natural logarithm of V of the over the capacitor. V of the capacitor equals minus t over tau plus ln V0. So once again, we see that this final equation gives a slope of minus 1 over tau, which is equal to minus 1 over RC. Generating a plot of ln VC versus t and producing a best fit line will give a slope of m equals minus 1 over RC. Therefore, the tau, the time constant, is equal to minus 1 over m. And I think that's, here's the procedure. I have both the charging circuit and the discharge circuit in one figure. So you configure the circuit shown in 1, and you complete the data header, close the switch, record the voltage on the meter at evenly spaced time intervals, such as every 3 or 4 seconds. Now, what I did is I had my iPad, and I put it in stopwatch mode, and then I had the voltage meter right next to my iPad, and I recorded the image of the whenever we flipped the switch, I started the stopwatch, and we recorded the video of the charge and discharge current, charge and discharge voltages, and then we reviewed the videos later, and we're able to get pretty accurate time steps of the charge and discharge. Okay, and that's what we did to record the voltage on the meter at evenly spaced time intervals. You plot a graph to get a best fit line. The charging time constant Tc should be approximately equal to the negative inverse of the slope. You do the same thing for the discharge. The discharging time constant, tau discharge, should be approximately equal to the negative inverse of the slope. And then you determine the percent difference between the calculated value of tau, in other words, the average of the charge and discharge. Oh, I'm sorry, the calculated value of tau that you put on your paper. That's this value here, and the average of the two time constant tau charge and tau discharge, calculated from the slopes of the two R1 C1 graphs. And then you pick two different values of R1 and C resistor and capacitor, and then you repeat the steps 1 through 12. And then here are the data tables for the charging of R1 C1 and the discharging of R1 C1. You put the negative inverse of the slope here, negative inverse of the discharge slope here, average them, and then you get the difference between this T1 average and your, I keep saying T, it's tau 1 average, and your tau 1 that you calculated. And then you do the same for the second set of resistor and capacitor that you chose. And that will end the discussion on this this laboratory exercise. Okay, and we'll stop the share and end the video. Take care.